Okay, great. So it's 2 p.m. and time to kick off the session. So welcome everybody to another session of NLA. We're very lucky to have two research talks today, which I'm really looking forward to. If you have any questions on Zoom, please ask them in the Q&A, which will be monitored by Minhong. Hi, Minhong. And if you're on YouTube, just ask them in the chat, which is going to be monitored by Marcel. Hi, Marcel.
Hi.
Great. So I'm really pleased to introduce our first talk today, which is from Yeva Darshkarte, who is a PhD student at the University of Reading on the Mathematics of Planet Earth Centre for Doctoral Training. And Yeva is going to be telling us about randomized preconditioning in data assimilation. So take it away.
Thank you, Jemima. Okay, so thank you for the introduction, Jemima. And this work today is joint work with my supervisors, Amos Wallace, Jennifer Scott, and Peter Jan van Leeuwen. And the aim of the talk is to explore using randomized eigenvalue decomposition to construct limited memory preconditioners for the forcing formulation of incremental reconstrained four-dimensional variational data assimilation. And these terms should make more sense soon. And during the talk, we will look at how to construct the limited memory preconditioners, and there will also be an idealized numerical example. So in data assimilation, we are estimating the evolution of the state of a dynamical system by combining observations of the dynamical system with a prior evolution of the estimate, So, and one application area of data assimilation is a numerical weather forecast, where data assimilation is used to obtain the initial conditions for the weather model. And in this application, the dynamical system may be, the size of the dynamical system may be 10 to the 9, and then we may have 10 to the 7 observations to assimilate. And there's usually a time constraint on how much time can be spent on the computations. So it is very important to do the computations efficiently. In this talk, we will look at the reconstrained 4D data assimilation method. Here we're looking for the states of the system over a period of time, hence the 4D. And in this method, it is assumed that a dynamical model, which governs the dynamics of the system, has errors which cannot be ignored. So the model is just a reconstraint here. And to obtain the analysis, the states of the dynamical system, we need to minimize the nonlinear cost function. And in the forcing formulation, we are looking for the state at the initial time and the model errors at the subsequent times. In the cost function, we have penalties for the discrepancy between the state at the initial time and our previous estimate of the state, which is called the background. We are also comparing the observations of the dynamical system and then the model variables mapped to the observation space. This is done with the observation operator H, which can be very complicated. And we need this because we may have observations of different variables than the model has. So for example, in weather prediction, we may have observations of the top of the atmosphere radiances, but the weather model operates on other meteorological variables, such as temperature, pressure, and so on. And finally, we have penalties for the model error. Each term of the cost function is weighted by the inverse of an error covariance matrix. We have B for the background, R for the observations, and then Q for the model error. So once we minimize the cost function, we obtain the analysis by integrating the nonlinear model and adding the model errors. Usually, integrating the nonlinear model is very costly. And as I've mentioned, in practical settings, the systems can be very large. So some approximations have to be made during the minimization. And one way to do that is to use the incremental method. Here we use bold notation for block matrices and vectors. So our vector P includes the state at the initial time and model errors, which we are looking for. And in the incremental formulation, we update our vector P with this increment delta P, and delta P comes from the minimization of a quadratic cost function. And we obtain the quadratic cost function by linearizing the nonlinear cost function that we have seen in the previous slide. Here we have the linearized model in matrix L, and H is the linearized observation operator. We also have the background and model error covariance matrices in the matrix D. And then R includes the observation error covariance matrices. So now we need to minimize the quadratic cost function. And this can be done by solving large sparse linear systems. And in the incremental method, we need to solve a series of these systems. And we have the system written here. And now the coefficient matrix of the system is the Hessian of the quadratic cost function that we've seen in the previous slide. The Hessian is symmetric positive definite. So the method of choice to solve the systems is the conjugate gradient method. And it is known that CG convergence depends on eigenvalue distribution of the coefficient matrix. And usually a clustered eigenvalue spectrum away from zero suggests rapid convergence. So to improve the convergence, two-level preconditioning approach is used. The first level preconditioning, we precondition with the square root of D. And now we have this preconditioned coefficient matrix. And in the rest of the talk, we will consider this matrix A. And so A now is a sum of an identity and a low rank matrix. This matrix is low rank because it includes the observation terms, matrices H and R, and it is usually assumed that the dynamical system is not fully observed. And the low rank matrix is also symmetric positive semi-definite, meaning that its eigenvalues are either 0 or positive. And so now this construction of A, the structure of A means that its eigenvalues are as follows. So we have a cluster of eigenvalues at 1, and these are also the smallest eigenvalues. And it is assumed that CG can take care of these eigenvalues well, so they're not problematic. And the rest of the eigenvalues are all larger than 1. And these are the eigenvalues that may slow down the minimization. And second level preconditioning is used to tackle these eigenvalues. So limited memory preconditioners have been used in data assimilation before. They have been used when preconditioning the strong constraint formulation. This is a formulation where it is assumed that the model has no errors. And limited memory preconditioners have been shown to be useful in these cases. So we consider these as well for our reconstraint formulation. And here we look at the spectral limited memory preconditioner, which is constructed using the eigenvalues of the matrix that we want to precondition and the corresponding eigenvectors. And usually the number of eigenvalues that we use, here we denoted with k, is very small compared to the size of the system. And spectral LMP maps the eigenvalues which are used in its construction to 1. And this is very useful in our case because we already have a large cluster of eigenvalues at 1. And this is true when we use exact eigenvalues and eigenvectors. But of course, for large systems, we cannot obtain the exact eigenvalues and eigenvectors, and we have to use their approximations. And even computing the approximations can be very costly. But what has been done in data assimilation is Lanczos and CG connection has been exploited. Because of this connection means that estimates of the eigenvalues and eigenvectors can be obtained cheaply after we solve the system with CG. And since in the incremental formulation, we have to solve a series of these systems, we can solve a system with CG, then cheaply obtain the estimates of the eigenvalues and eigenvectors, and use these estimates to construct limited memory preconditioner for the consecutive system. So however, this will only be useful when the coefficient matrices do not change significantly in the consecutive loops. And there are advances in data assimilation where new information is introduced throughout the series. So this may not be useful anymore. And for that, we suggest to look at using randomized eigenvalue decomposition. So in previous years, randomized methods for low rank approximations have gained a lot of attention. And it has been shown that these algorithms give accurate approximations with high probability when the eigenvalues decrease rapidly. These methods are also easy to implement, and they are block methods, so we can easily parallelize the required matrix products. And because of these reasons, we suggest to use the randomized eigenvalue decomposition to estimate the eigenvalues and eigenvectors of the coefficient matrix, and then use these estimates to precondition the current system. So we wouldn't be using the information from the previous system. And I do not show the method itself here, but the randomized eigenvalue decomposition returns k estimates of the largest eigenvalues and eigenvectors of the coefficient matrix. And the methods can be divided in two stages. So in the first stage A, we compute an orthonormal matrix Z such that the range of the coefficient matrix is well approximated. And then in the second stage, we use this orthonormal matrix to compute a standard eigenvalue factorization of our coefficient matrix. And this includes computing an eigenvalue decomposition of a small matrix, which is usually cheap because we want to use just a few vectors in our preconditioner. And the most important expensive parts of these methods are the matrix-matrix products. There we have one product in each of the stages, but these as I've mentioned, the matrix-matrix products can be parallelized well. Okay, so now we will look at a numerical example. We use identical twin experiments, which means that we generate a trajectory of the dynamical system and we assume this to be the truth. And we use a Lorentz 96 model, which is a common choice in data assimilation experiments. It has 80 variables, and we run the system for 150 steps. So the size of the linear system that we solve is around 12,000. And we generate the error covariance matrices for the background model and observations. And we have direct observations of the dynamical system. We generate this by adding by adding noise to the truth state. And then we have 120 observations in total. And in our experiment, we want to compare using randomized method to what is available now. So we do as follows. We solve the first system without any limited memory preconditioners. And then in the second system, we construct the limited memory preconditioners in two ways. We call the first one the deterministic LMP. And to construct this preconditioner, we use a MATLAB function eigs to estimate the largest eigenvalues and eigenvectors of the coefficient matrix that arises in the first system. So eigs gives a high quality approximations of the eigenvalues and eigenvectors, and we assume this case to be the best, so the best preconditioner that you can obtain if you use the information from the previous system. And then the second way to construct the limited memory preconditioners is using the REVD, so the randomized eigenvalue decomposition. We run the randomized method, obtain the eigenvalue estimates for the coefficient matrix in the second system, and then we use these LMPs to solve the system. We call this approach the randomized LMP. And so to be sure that we are not just lucky with the randomized method, we run this 50 times using different random seeds for the method, and we report on the mean values of the quadratic loss function at every iteration. However, in practice, you wouldn't need to do that because all the runs were quite close to the mean. And so experiments are performed with MATLAB. And here we see the results. Here we show the quadratic loss function value at every iteration of the precondition CG when we solve the second system. So here with the black line, we show the case where we use no limited memory preconditioner. We use dashed lines for the cases where we use the deterministic LMP. So when we obtain the eigenvalue and eigenvector estimates when solving the previous system. And then for the randomized method, we use the the dotted lines here. And the limited memory preconditioners are constructed with either 5, 10, or 15 vectors. And there are two things that I want to point out here. The first one is, of course, that using randomized LMP, improves the minimization compared to both using no limited memory preconditioner and using the deterministic limited memory preconditioners. We can see that using the randomized vector, the randomized LMP, which was constructed using 5 vectors, gives us faster minimization than using the deterministic preconditioner that was constructed using 15 vectors. And also we get a large improvement in the minimization in the first iterations, which is important because we may be able to run just a fixed number of iterations. And then the second thing that I want to point out is that increasing the number of vectors used to construct the limited memory preconditioner gives us better minimization if we use the randomized method. Well, this may not be that noticeable if we go from using 10 vectors to 15 vectors in the beginning, but we see the improvement later on. And if we use the deterministic LMP, then there is not much improvement if we increase the number of vectors used to construct the LMP. And to summarize, we looked at second-level preconditioning for the forcing formulation of the incremental weak constraint for the var. We've seen that randomized methods for low-rank approximations, well, namely the randomized eigenvalue decomposition, can be used to construct limited memory preconditioners, and this can be done independently of the previously solved system. And our simple numerical example shows that randomized preconditioners can be more effective than currently used techniques, and using more vectors to construct the randomized LMP results in faster minimization. And some further work, we have done some of it. So in our manuscript, which is available on arXiv, we test 2 other randomized methods to construct the limited memory preconditioners. And then we also explore the sensitivities to the number of observations of the dynamical system. And then something we haven't done, but we think that it would be very interesting to test the randomized preconditioning for larger and more realistic systems. And here are some references. I'll just go back to the summary. So I'm happy to answer any questions you may have, and thank you for your attention.
Great, thanks for that, Yeva. That was really interesting. I might start with a question, which is, so increasing K a little bit, you do see a benefit in terms of convergence, but is there an associated increase in computational cost with that?
Yeah, of course. So, but the increase in the cost is not very large because we just need to do so if I just go back to the definition, how we define the preconditioner here. So we would just use more vectors here, and we would need to do, if we increase the K, we would need to do more vector-vector products with the preconditioner, but the K is quite small, so it's not a big, so we assume that the largest cost in CG is the matrix products with our coefficient matrix. So a few vectors here would not be that expensive.
And I guess relatedly, how is it? Do you think it's just going to be a matter of choosing K in an ad hoc way, or do you have some idea of how you could choose it a priori?
No, so we don't really know how to choose it a priori. I suppose it would depend on the memory and the
problem and
the problem as well.
Great. Are there any questions from Zoom, Minhong?
Yes, there's a question from Huzam. How can you explain that the approximation obtained by eigenvalues works better than the randomized approach? At the end, eigens should give accurate approximation, but more costly eventually. Thank you.
So I'm not sure. So here we use the eigs to estimate the largest eigenvalues of the system that we solved in the first loop, so not the system here. And in practice, of course you wouldn't use eigs. You would obtain the estimates cheaply after you solve the system because of the Lanczos and CG convergence. So you do get you can get a good estimate of the eigenvalues and eigenvectors, but it is a good estimate of the eigenvalues and eigenvectors of the coefficient matrix that was solved before. And now we updated the coefficient matrix when we solved the second system. So I'm not sure if that answers the question.
Well, I'm sure Hassan can ask you afterwards if he wants to follow up on that. Marcel, do you have any questions on YouTube?
Yes, we have one question. I don't know by whom because I only see a cryptic nickname. So the question is, you've shown average precision for the cost, and do you have some asymptotic results on the concentration of the probability when the dimension is big?
No, we don't. It may be interesting to do it, but well, at the point we don't have it.
Okay. Yeah, that's it from YouTube.
Brilliant, thank you.
Jemima,
yeah.
Huzam want to speak?
Oh yeah, sure, go for it.
I think in the interest of time, I'll skip my questions now. We can discuss that.
Great, cool. Well, thanks for that, Yeva. That was really interesting.
Thank you.
Okay, and now time to move on to our second talk. I'm also delighted to introduce Kirandeep Kaur. Kirandeep is a PhD student at the Max Planck Institute for Dynamics of Complex Technical Systems in Magdeburg, and she's going to be telling us about TTCP, an approach to efficient machine learning model. So take it away when you're ready.
Can you hear me now?
Yeah, that's great.
Yeah, okay. Thanks a lot for the introduction, and thanks for the organizer for organizing this seminar. So, okay. So I will be talking about tensor trained canonical polyadic, aka TTCP approach, which is an approach to efficient machine learning model. And this is a joint work with my supervisor, Professor Peter Benner, and my co-supervisors, Sergey Dolgov and Martin Stahl. And I will be talking about not about like numerical linear algebra, rather numerical multilinear algebra. So throughout my presentation, I will start my work, my talk with a motivation, like what's the motivation behind my PhD work. And then I will tell about the machine learning models, how we are building that, and then how the tensors and low rank approximation helps there to build this machine learning model, and this building efficient model, and what does it mean by efficient model. And after that, I will give some numerical results to just support the algorithm and the work which I would present during this talk. And I will end my talk with some conclusion. So for the motivation of my work, if you see, this is an example of a brain fMRI image data set. This is a resting state fMRI data. And so this, so if you see here in this image, like the data set has a 4-dimensional data. The 4th dimension is the time, and each, the 3 dimension has this voxel, which is volume, pixel with the volume. So this data set has like a multidimensionality, and most of the cases, this medical data set doesn't have a large amount. Like this, the data set is small sample size. So what does it mean? Like I have a data set which is a small sample size, and also have a constraint of multidimensionality. So what do I want to do with this data is to build a binary classification in terms of, like, I want to see just by looking at this data set or this fMRI data, that a person is a healthy person or has some particular disease. So it's like a 1 and -1 classification model. So for that, we need a learning model. And also here we assume, or that's also in general true for the real world data or the medical data sets, that the classification is nonlinear. And I will explain what does it mean by nonlinear boundary here. So we need a binary classification learning model with nonlinear boundary for the small sample sized and multidimensional data set. Along with it, we also need this model to be an efficient model, efficient in terms of robustness and robustness in terms of the rank of the this multidimensional data. And also we need like the higher accuracy, higher classification accuracy, and it should also give a state-of-the-art machine learning model for that. So first I will start with the small sample size, like what does it mean by small sample size and how we deal with small sample size in machine learning model. So as I said, we have this binary classification. For that we have an input X and then output is 1 and -1. And for the learning model, we use support vector machine. So support vector machine is basically well-known kernel method to classify the data. Especially for the binary classification, and this was a state-of-the-art method before neural network before neural network, and also for the nonlinear boundary, I will explain like how to use this projection onto higher dimensional space. So first, I will talk about the support vector machine. So support vector machine, if you see here, this is basically like classifying two different type of data set with this hyperplane. And this hyperplane is, it's on the maximum distance from these two support vectors. So these planes are known as the support vectors. And the plus point of using support vector machine is that we deal only with these points which lie on these support vectors and known as on these support vectors. So that's the one benefit of using support vector machine, because it's computationally cheap compared to other classification model, just because we are dealing with only these support vector points. So how do we build a model for the support vector machine? So as I said, support vector machine is a hyperplane which classify the maximum margin distance. And for the input data, we have a output label -1 and 1, and we need an hyperplane L. And we do that by using this hypothesis. What does it mean by? So we kind of take the sign of this inner product and then we add some bias, and then we check if the sign matches to the label or not. So if it's -1, then belongs to one class, and it's 1, then it belongs to the other class. So that's the basic idea of support vector machine. And if I write this support vector machine in optimization format, so this formula will come where xi I are the slack variables. And mostly in SVM, this support vector machine are known as SVM. So this SVM, we use dual optimization problem. And I will explain why we work with dual optimization problem. And when we take the Lagrangian of it and then compute the dual of SVM. So now we have a binary classification learning model for small sample size data. Now, second thing, what we want to add the nonlinear boundary here, right? So for the nonlinear boundary, what we do, we take a data from a lower dimensional space and then we project it into the higher dimensional space. And in the higher dimensional space, the data is again linearly separable. So that's the idea we used here. And how do we do this in this optimization problem? So that we just replace this the input values, the xi and xj, by phi of xi and phi of xj, where phi is this nonlinear mapping. Now question arises like how we compute this function phi. Like if we compute this function phi explicitly, so it would be not like an optimal way of doing it. That's why we use this dual optimization problem, and then we approximate this inner product of function phi with a kernel matrix or kernel function. And this algorithm is, this approximation is also known as, comes from this representation theorem, and it is also well known in machine learning community. And so this is basically like high dimensional implicit feature space and without ever computing this in original coordinate space, we are approximating the values. So that's the idea. And then when we include this idea into support vector machine, so we get this final nonlinear boundary optimization problem for solving support vector machine. So by now we have a model for binary classification nonlinear boundary learning model for small sample size. And now next constraint is we want to add the dimensional data here. So how do we deal with multidimensionality for the support vector machine? So maybe we just replace this thing, and if we replace, then how we can compute this kernel for this multidimensional data. And also in the vector cases, this kernel can be like any kind of function. Mostly we use this radial basis function because this radial basis function basically provides value between 0 and 1. 1 when the two values are close or maybe in the same label and labeled class, and 0 when they are apart. So that's the idea, and that's why we use this radial basis function here. And now, so why we use this dimensional data and how we use it in support vector machine. So first of all, tensor is a multidimensional array. So what does I mean by tensor? So it's like these are the slices. This is an example of a 3-dimensional tensor. You can consider like RGB image, and we can go up to the n dimension tensor. So, and we know that tensor has a power of structure exploitation. So basically, like we can take the whole data and all together, and these data points are somehow have some structure and related to each other. So we can use that directly by using the tensors. And when we compute the tensor decomposition, as tensor itself has curves of dimensionality, so tensor decomposition are computationally efficient also. And all the problem with support vector machine, when we use tensor, the first idea comes to our mind, okay, we can convert tensor into the form of a vector and then we can apply support vector machine. But somehow the data loses its structure. So that's actually not feasible to do with the support vector machine. And also we have availability of tensor toolboxes, so we can make use of that, and it makes implementation easy. And there is an extension of SVM for the tensors, and it's called support tensor machine. And support tensor machine works directly with tensor as an input. So if I take all these points and take the support vector machine dual optimization problem, then I reach to this dual nonlinear boundary optimization problem support tensor machine for the tensor input data. And the only difference here is that we have this kernel function over the tensor input, and other things are almost same here. So if we are able to compute this kernel, and also we are able to compute this kernel efficiently, then we are done here basically. So now the idea for computing this kernel for the tensor is we can like proceed with that. But before that, I would like to give the idea of like a low rank tensor decomposition. Why? Because we know that tensors has this curves of dimensionality, and tensor decomposition works efficiently with the curves of dimensionality. And especially here, we are using tensor train decomposition to provide a compact form with a low amount of storage. So tensor train decomposition is basically like dividing a big tensor into a small tensor, 3-dimensional tensor blocks. And all the algebraic structure which are possible for this big tensor can also be inherited in this small tensor, small 3-dimensional tensor. So that's the idea of tensor train decomposition, and mathematically it can be written in this form where R0 and Rm are the ranks, and they go from 1 to Rm. And these are the TT cores. The G1 and GM are known as the TT cores. Now the kernel computation. So if I go back to the literature for this kernel approximation in tensor format, So the first idea was done for the canonical polyadic decomposition. So canonical polyadic decomposition is basically rank one sum of the sum of the vectors which approximate this three-dimensional tensor. And so this idea first was used, Lifang He and other authors in the paper, and it was known as the dual structure preserving kernel. So what they do, they take the tensor data from tensor space to the tensor reproducing kernel Hilbert space. And the point is, when you do this, so basically this mapping, so basically like inner product of this mapping, which is by representation theorem, can be written as a kernel of these two tensor input, can be computed by computing the kernel over these vectors basically and sum over the rank. So rather computing kernel for the big tensor, we are now just working with the small vectors here. So that was the idea for the dual structure preserving kernel. Now, we wanted to use the same idea for the tensor train decomposition. Why? Because tensor train decomposition has a stable algorithm. And the ranks also depends on the matrix SVD, which is generally not the case for the CP decomposition, because in CP decomposition, finding a best low rank approximation is an NP hard problem. But the plus point of the CP decomposition is its simplicity, and also this dust kernel was somehow prone to the CP decomposition, CP format. So what we did, we combined the idea of using the stable algorithm with the CP simplicity of the CP decomposition, and then we implemented this TTCP decomposition, in which the first step was converting the tensor train, like a direct expansion of a tensor train, to the CP decomposition. And it's known as exact TTCP expansion. Exact because here we are basically just merging the rank and then changing kind of a format of tensor train to CP format, to CP expansion. And we are not like, we don't need extra computation for that. So that's why just exact TTCP expansion, and we do just by taking this, just by merging these rank, and then we can get TT into the form of a CP. But after doing that, another thing we added was uniqueness enforcing TTSVD. So the point here is this uniqueness enforcing TTSVD means the TT decomposition was computed by Ivan Osilidate's TTSVD algorithm, but there for the TT decomposition, the singular vectors, the singular value decomposition, if you see here, the singular value decomposition, this U1 and V1 could be of like minus U1 and minus V1. So that's why we wanted to fix the sign of this singular vectors. And we said that this uniqueness enforcing means uniqueness in terms of the sign for the singular vectors. And so this somehow gives us a closed tensor produces closed TT course. That means like if two tensor are in the same label class, then their TT decomposition, if we compute the kernel approximation for that, that should also be in the same class. So that was the idea. And the third thing we did was applying the norm equilibration. Why? Because the CP decomposition, when we compute by using ALS, this alternating least square algorithm, the norm is equally distributes to each core of the CP decomposition, while that is not the case in the TTSVD. And when we are computing kernel, so we are using each vector for the kernel computation. So that's why it's really important to have equally important vector. So that's why we distribute the norm equally on each vector of the TT core. So by combining these three steps, we apply this support and this We compute the kernel approximation by TTCP, and we call this method as a tensor train multi-level kernel. So just to summarize the idea, what I did, we have an input tensor. We want to compute the kernel approximation for that. So first we compute the TT decomposition for each data point. And then we compute TTCP decomposition, which includes uniqueness enforcing TT-SVD and also the norm equilibration. And then we plug that data into the kernel, and then we sum over the rank, and then we have this kernel matrix, and then we plug back this kernel matrix into the support vector machine. So by doing that, so how I'm setting up my numerical experiment. So I'm using two different data points, and if you see two different data sets, Alzheimer's disease data set, and these both are the resting state fMRI data. And if you see, we have only 33 data points. So it's not actually feasible to use neural networks here. So that's why we, as I said, like we have a small sample size problem. So these 33 data points, we use the tensor train toolbox for TT decomposition, and then after getting this TTCP approximation, we use this libsvm library for the support vector machine. That means just optimizing the support vector machine problem and then predicting the label. And we use k-fold cross validation for splitting training and testing data among these like 33 data points, and also use the grid point search method to find the best C and sigma. And for the parameter tuning, we had 3 different parameters: TT rank from 1 to 10 we took, and Gaussian kernel, which was for the radial basis function, and also the trade-off parameter in the support vector machine optimization, this objective function. So after setting up all this experiment, we had this result. So if you see, when I apply only the TTCP expansion, then the stability is not good. The accuracy is still like fluctuating a lot along the rank. So this is rank versus accuracy, the classification accuracy. And when we applied this uniqueness enforcing TT-SVD, then you can see that like there is a significant difference in the robustness or the stability with respect to the rank for to the accuracy. And when we added the norm equilibration, then there is a clearly the increment in the accuracy. And this is a comparison with the method which uses the CP decomposition. So in our method, if you see, like for the rank 2 also, we are almost getting like not the best, but still the better accuracy than the rank, than the CP decomposition. And even for different ranks, the accuracy is not fluctuating a lot. So that's how we can say like our method is more robust with respect to rank, and it's more efficient. So these are the comparison I did. So if I just directly use support vector machine, so it doesn't produce anything, like just converting the tensor into a vector format. And also this is a comparison with CP, and this is multi-way, multi-level kernel. So we are using kernelized CP decomposition, and here we are using tensor train CP decomposition. With this, I would like to summarize my work. So we introduced a low rank method called TTCP decomposition, and we also introduced a binary classification kernel model for a less data, for small sample size with multidimensional input. And approximating kernel, we have seen not only reduces the cost, but also increases the accuracy and stability and reduce computational cost with higher accuracy. And I have used these toolboxes, and if any of you is interested, you can have a look at the paper. And with this, I would like to thank all of you for your time.
Great, thank you. That was a really nice talk, Kirandeep. Minhong, do we have any questions on Zoom?
Yes, there's a question from Deepak Prasad Dula. How the efficient rank is chosen for this case? I guess the numerical result.
Okay. So actually we just took like from 1 to 10, and then we run the experiment. So it's not like we are choosing specifically. but we are just like running the experiment and then seeing like which one is giving the best accuracy.
I had a question about these results as well.
Yeah.
So the two experiments you've shown here, the ADNI was the one that only had 33 samples and the ADHD had more. Do you see a difference in how the performance is, or is it that both of those are small in comparison to the dimension of the problem?
You mean like if I increase the number of data points? So
yeah.
Actually not. Like if you see here, we are getting like lower accuracy compared to like the ADNI. Even like the lower the less the data, the better the results we have. But still, I cannot like generalize this thing. Like if I have a more data, then I will have better accuracy or a less accuracy. I cannot say that.
There is also a question from Hannah Ritesh. How did you compute the accuracy?
How did I compute? So for the testing, so for the training, first we build the model. And then for the testing, we see if the prediction is correct or not. So that's how we check accuracy.
Cool. Marcel, did we have any questions on YouTube?
No, there are no questions on YouTube.
Okay, great. In the interest of time then, I think we'll say thanks to Karandeep for the great talk. And if you have any questions, please join us on Gather after the session. Okay, so that is the end of today's session. Let me do a quick plug for the next session in 2 weeks' time. So it's going to be on April the 26th, and we're going to have a mixed session. We're going to have a talk from Andre Gall, who's going to be telling us about startups and a publishing house that he's founded. And we're also going to be having a research talk from Spiros Koukakiotis from the University of Edinburgh. So please join us there for 2 more talks. And in the meantime, hopefully see lots of you on Gather in a little while. And thanks for the 2 great talks today.